Hi everyone, this is Ranjit and welcome to the 7th video in the GeomAlgoLib series where we continue with our ConvexHull algorithm. Okay, so let's just jump right in and create the PInvoke method that we are going to need to start using our ConvexHull code from inside our C# project. So let's just move to the ConvexHull header file and write the declaration for our PInvoke method. To begin with, let's just make the return type void and call the method unsafe create ConvexHull, and we're going to need, all we need is just the initial set of points, right? And they're going to have to come in as a flat array of coordinates. And because it's a pointer, we're going to have to know the number of points. And that's essentially all we need to create the ConvexHull. But then we're also going to have to return the created ConvexHull back to C#, or else it's kind of pointless. Well, not really, because it's got a lot of points in it. Sorry about the joke. So yeah, now let's think about the return parameters. So the points are already present on the C# side, right? Because that's where the points came from. So we don't need to communicate the points of the ConvexHull back to C# again, because the points are there. It's just redundant. So all we need to do is communicate the indices of the vertices that make up the triangles of our ConvexHull. So essentially all the triangles. So let's just return that as an integer array. It's just a flat integer array of face indices. And because it's a pointer, we're going to have to know the number of triangles or number of faces. They're obviously triangles, so let's just call them n faces. So that's the signature of our PInvoke method. And now let's add the definition in our source file. And we already have the coordinates as a pointer and the number of points, and that's all we need to create the ConvexHull. So let's just create that using our constructor. So now that we have the ConvexHull, the constructor automatically calls the compute method, which means by the time this line of code is finished executing, the ConvexHull is already computed. So all we need to do is get the data. So number of faces can be, we can get that by calling the hull numFaces method. So now that we know the number of faces, we can initialize the face indices array to 3 times the length of the number of faces, because each face will contribute 3 indices exactly. And now that we've initialized the face indices array to the correct length, we can call our hull.copyFaces method and pass the pointer to have all the face indices copied to this array. And this array is passed by reference, which means the data should be accessible now from the C# side. So let's build our C++ project one more time. It builds without errors. Great. Now let's jump into our C# code and start using our PInvoke method. So the first step is to jump into our unsafe.cs file and write the declaration for our PInvoke method. So we're going to once again do our familiar DLL import with a calling convention of C-style declaration. It's going to be internal static, just like the other method that we used for testing. And the name is unsafe create ConvexHull. And the first input parameter is a flat array of doubles with the coordinates of the points. So it's going to be double coordinates. And the second is going to be the number of points. And let's see, did we use size t or integer? So it looks like we've used size t, which means we're going to have to use ulong here. And the third is is an integer pointer passed by reference. Face indices, and the fourth is an integer that is passed by reference, which is the number of faces. So that's everything, but there's one small thing that we also need to do. The array that we're passing here, we're going to add an attribute to this parameter, Marshall as unmanaged type LP array. So this is going to tell C# how to transfer the data inside this array between the managed and unmanaged code. So now let's jump back into our test.cs file and add another public static method to test our ConvexHull algorithm. And this method is going to return a mesh and create ConvexHull is what we will call it, and it's going to take an I enumerable of 0.3D objects. Okay, so the first thing we need is a flat array of coordinates. So we're going to get this array using link. So for each point, we're going to get a flat array of its coordinates. And then, because we're using the select many, that all the coordinates get flattened into one array, and we have to of course use toArray thing at the end to make it an array. So we've got the all the coordinates, and let's just get the number of points. And what else do we need? We need to initialize the variables that we will be passing as return parameters to our PInvoke call. So let's just create those pointers. One is for face indices. Let's initialize it as a 0 pointer. And another is just an integer for the number of faces. Let's just initialize it as 0. So let's finally make our PInvoke call. The name of this method seems a bit redundant because we already have unsafe in the class, and then unsafe underscore just doesn't make sense, so maybe I'll go back and change the name, but I'm just going to leave it as it is for now. So we're going to pass the coordinates, then number of points, then pass as a reference the pointer to our face indices, and then also passing by reference the number of faces. Okay, let's call it n faces. And what is the problem with this? Cannot convert from int to ulong. So let's just create a ulong type first. Oops, I changed the wrong thing, sorry. Okay, so that should fix it. It does. So now let's just rename this function as ConvexHull_create. And let's just take that name and go back into our C++ code and rename it there too, because they have to match. Okay, that seems to have worked. Cannot implicitly convert type int to ulong, so let's just cast. And after we've finished making this call to the PInvoke unmanaged code method, we got these return parameters back. Well, they're populated with some useful data, so we have to extract that data. So let's create an array for face indices. In fact, let's name this face indices pointer, and let's name the array that we're going to create face indices. And we know the length of the array because we know the number of faces, which is also a return parameter. And let's make the array 3 times as long as the number of faces. And let's use Marshall.copy. Okay, looks like there's no... That's annoying. So we're going to have to add a using directive at the top for system.runtime.interrupt services. And that allows us to use Marshall.copy to read the data from our pointer. So the source will be our pointer itself, and the destination will be our array of face indices. So let's find the right overload. It looks like that's the overload we're looking for. Okay, yeah, okay, that's the 10th overload out of 16 overloads is what we're looking for. Start index will be 0, and the length will be the length of the array. Okay, looks like we misspelled the face indices array. Let's just change the name. Okay, that copies all the face indices. And now that we've copied all the face indices, we have to responsibly delete the allocated memory on the unsafe side in our unsafe code. So, okay, to do that, we have to actually add those methods to our unsafe class. So let's go back one more time to our base.h header file. And yeah, let's just rename these methods because having this unsafe prefix is sort of redundant. Let's just rename this to release int. And this one should be simply release double. And I'm just going to copy the signature and add it to my unsafe.cs file. Bool is going to stay the same, but the array, okay. This is actually a pointer, so we have to make it a pointer. And let's add the DLL import attribute. What is wrong? Oh, okay, we forgot the internal static thing. And it doesn't return anything, so. And then similarly, we're going to have another method to release doubles. Everything is the same because on the C# side, a pointer is just a pointer. It doesn't matter whether it's double or int. It only matters once it gets to the unmanaged code. So let's just name it release double. So we can just use these two methods to responsibly clear all the memory that we've allocated in our unmanaged code. So here, once again, we're back in our main method. We copied all the face indices, so we are ready to release this array. It's an integer array, of course, and we're going to pass the pointer. And it is an array, so we're going to say true for the second parameter. And once we've deleted the memory, we can actually try and use these indices to create our mesh. So let's initialize a new empty Rhino common mesh. The indices that we got in this array that represent the faces, they are the indices in the list of all of the points, right? Like the whole collection of points. So this mesh is going to have all the points. So in fact, you know what? I'm going to convert the enumerable that we get into an array right at the beginning so that it's more efficient. I'm going to call it PDAR for PDARR, representing point array. And I'm just going to use the array because it's faster instead of using an enumerable over and over again. Okay, so we're going to add all these points as vertices to our mesh. And then we're going to loop over our face indices and add all the faces. So we're going to create a loop with the number of iterations set to the number of faces. And for each face, let's just add a mesh face with the face indices. And finally, 3 times fi plus 2. Okay, we have added all our triangles to the mesh. And let's just rebuild the mesh normals, because that makes the mesh look nicer in, when Grasshopper renders it. And then just return the mesh. We're done. Maybe one more thing that we want to do is actually time how long it takes for our ConvexHull algorithm to work. So let's add a system.diagnostics using directive at the top. And let's create here, just before we make our first PInvoke call, let's create a stopwatch and start it right away. And once we finish adding all the faces to the mesh, let's stop the watch. And we're going to have to get the stopwatch elapsed milliseconds and elapsed ticks somehow to Grasshopper. So let's just create a couple of out parameters. Elapsed milliseconds, elapsed ticks. And we're going to set these two out parameters to what our watch recorded. Okay, so that's everything that I can think of right now that needs to be done. So let's just build both our projects and see if everything builds correctly. So it looks like it builds without any errors. And the next step is to load this up into Grasshopper, use it from a C# component and see if it works. And because we set up our initial project configuration to use Rhino for debugging, we should be able to just press F5 and it should put Visual Studio in debug mode and start up Rhino. And let's just start working with a new file. Let's create a new C# component, and all this component needs to take is the list of points. It's going to have list axis, and the type is going to be of point3D. And let's add our assembly. We already have it here in our recently used assemblies. So we should be now ready to start using our C# DLL from inside the C# component. So let's try and access our namespace. Yep, works. So our class is test.createConvexHull, and let's pass the points. And we have two out parameters which give us the performance numbers, long, ms, and ticks. So let's pass them here, out ms and out ticks, and let's print the data, performance data that we get. Now let's set the mesh that we get to the output parameter A. Okay, so let's see if that works. Well, it's not going to work because there's no points. It's going to throw an exception. Yeah, so this is the exception in our createInitialSimplex method, because we have less than 4 points, we actually have 0 points, so we throw an exception. So let's just deactivate this component for now and think about creating a collection of points. Okay, there we have our collection of random points, 500 random points. Let's plug those points into our C# component, turn off the other displays and see what we get. Okay, another exception. So looks like when we try to add this face to the edge, we are not able to actually add it. Okay, so I had to pause the recording to figure out what the reason for this bug was, and I traced this bug back and I found a mistake in our code. Here, when we are creating our initial simplex, we are taking the 4 best vertices that we found and creating 4 faces from those 4 vertices. And if you look at line 317, what we have here is vertex number 1, vertex number 2, and once again vertex number 2, which means we are creating a simplex with one of the faces being degenerate. This was a typing mistake. It was supposed to be 0, 1, 2, 0, 2, 3, 1, 2, 3, and 0, 1, 3. So now our simplexes are being created correctly. Let's just rebuild both of the projects and restart Rhino in debug mode one more time. So here we have our file open one more time. This is our collection of random points, 500 random points that we are plugging into our C# component that uses our C++ algorithm. And yep, looks like that generates the convex hull. Just to make sure that everything is convex, I am going to turn off the Grasshopper preview, bake the mesh, and go into a rendered view. And as you can see, you shouldn't see any edge that indicates a valley, so it should be strictly convex. Yeah, it looks like our algorithm is running successfully. And let's look at the performance numbers that we were printing out. Okay, so computing this 500 point hull takes 24 milliseconds. But this is not actually a reliable number because we're in debug mode. Okay, so now if we go into our C++ project properties, if we go into C++ and optimization, if we look in debug mode, the optimization is disabled. But if we look in the release mode, it's set to maximum optimization favor speed 02. So because of that, in release mode, the C++ DLL is going to be highly optimized and it's going to be much faster. So let's switch to release mode and rebuild the C++. Well, in fact, we should have rebuilt both projects. Let's do that. Okay, so both projects are now rebuilt, and let's reopen the same file. So that gives us 3 milliseconds time instead of 24. But actually that is also not very accurate because the first time you run the function, it has to find the DLL on the disk and load it. So if I run it again, that brings the time down. And it's actually very fast. It's like half a millisecond. And let's turn off the preview for the points. And let's actually increase the number of points all the way up to 1000. And our algorithm is still very fast. It's sub-millisecond for 1000 points. Okay, so I had to pause the video one more time to check why the performance was a bit off. So I looked over the code one more time and tried to find anything that we do that is redundant and can be improved upon. This was actually a necessary change because this was sort of a bug. We forgot to do this in the first place. So after we pop all the visible faces in our, okay, just for the context, this is inside our compute method, and we popped all the visible faces and collected all the naked horizon edges in this vector. Just before creating new faces, like one new face for each horizon edge, in our original implementation, we completely forgot to clear this new faces vector. So what we were doing was, in each iteration, we were just accumulating new faces in this vector over and over again. I realized the mistake and added these 2 lines of code. So now before we actually start creating the new faces, one each for our horizon edges, we clear the new faces that we created before, and we reserve the space for the new faces because we already know how many new faces we're going to be creating. And with these 2 performance optimizations, I expect the performance to be significantly better than what it was last time. So let's rebuild. So as you can see, we get reliably under 5,000 CPU ticks. So it's always between 4,500 and 5,000 CPU ticks for a convex hull of 1,000 points. And if we zoom out to look at the hull and actually use this number slider to, increase and decrease the points, it's quite responsive. And obviously, because even the 1,000 point hull only takes 4,000 or 4,500 CPU ticks. So let's actually bump the number up and try 10,000 and see what happens. And that took 3 milliseconds. It's pretty good. And let's increase it tenfold one more time. That took 30 milliseconds. So it's almost proportional. And because we're populating this single box with so many random points, we're starting to approximate the volume of a cube. But yeah, ConvexHull works, and I'm going to call this a success. That's pretty fast. So that wraps up the ConvexHull algorithm implementation, and obviously all the code is in GitHub. You should be able to find the link in the description. Thanks for watching this video, and hope you find this helpful, and hope you actually find uses for this ConvexHull algorithm, whether it be the code that we wrote in this repo itself, or maybe you understood the algorithm and you are able to implement the algorithm yourself again in a different language, maybe in Python or whatever. So yeah, with that I'll conclude this video. Thanks for watching, and I'll come back to you next time with the next algorithm for our GeomAlgoLib series. Bye.